In today's class, I wanted to talk about a particular class of electrical circuit. It's a class of circuit that involves batteries and resistors. Specifically, I'm going to introduce the idea of batteries and the related idea of electromotive forces. That'll be our first topic. I'm going to discuss circuits that contain resistors in series with one another and circuits that contain resistors in parallel with one another. That's our next topic. And then finally, towards the end of the class, we'll talk about more complicated circuits that have combinations of resistors in parallel and series. And so that's the overall plan for today's class. So here's an example of a circuit that we're working towards understanding. So this is a circuit that contains on the left a battery, indicated by the circuit symbol for the battery. And then it contains a number of resistors, indicated by the circuit components for the resistors. And actually in this circuit, we've got cases where resistors are in parallel. We've got cases where resistors are in series with one another. And we've got a battery, an electromotive force source. And this is the type of circuit we want to understand. The sort of things that we want to understand are how is the current delivered by the battery distributed through the resistors? How is the voltage delivered by the battery distributed across the resistors? How's the power and energy that's supplied by the battery dissipated across the circuit components? If you wanted to think of an example of this type of circuit, all you got to think of is your household wiring in your home. So your household wiring in your home has a supply, is attached to a supply of electrical current, electrical voltage, and it distributes electrical current, electrical voltage to appliances in your home. It distributes the voltages and the currents to the lights in your home, to the heater in your home, to the hairdryer in the bathroom, to the microwave in the kitchen, and so on and so forth. And so that's a classic example of an electrical circuit with a source of voltage, a source of current that's being supplied, delivered to a number of different circuit components that are arranged in parallel, are arranged in series. So the first thing we're going to talk about is batteries and electromotive forces. Batteries are suppliers of electromotive forces. Actually, the name electromotive force is a poor choice of name because the electromotive force is not actually a force. For example, the units of electromotive force are the units of volts. And we think of the electromotive force as a source of voltage in an electrical circuit. The reason it's called an electromotive force is because it's a force that comes from the chemical reactions in the battery that are actually lifting the electrons from one terminal of the battery to the other terminal of the battery so that they can become the current in the circuit to which the battery is connected. So inside the battery, the electrons are moved from the positive terminal of the battery to the negative terminal of the battery. And they're moved from the positive to the negative terminal of the battery by the chemical reactions that are occurring in the battery. And that's what we think of as the electromotive force. You can think of those chemical reactions as lifting, as raising the electrons from the positive terminal, where they would have less electrical energy because they're attracted to that, to the negative terminal, where they have more electrical energy because they repel from that. By lifting the electrons from the positive to the negative terminal, by raising the electrons from the positive to the negative terminal, you're giving the electrons the ability to flow around the circuit. So that chemical reactions, that electromotive force, is enabling the electrons to then flow around the circuit, be the current around an electrical circuit. On this slide, I want to introduce real batteries and ideal batteries. And so on this slide, we've got on the left-hand side a circuit diagram that involves an ideal battery, and on the right-hand side a circuit diagram that involves a real battery. And we're going to discuss these two circuits, these two circuit diagrams, and introduce some terms like EMF, like load resistor, like internal resistor.
Here that is a circuit diagram for an ideal battery. And then there's a corresponding one on the right-hand side that is a circuit for what we call a real battery. Now, in these two diagrams, there's some quantities that I want to introduce. So there's the EMF. This symbol epsilon is the EMF, the electromotive force for the battery. Here it is for the ideal battery. Here's the EMF, epsilon, for the real battery. And then there's also some resistors in these circuits. This resistor downstairs, the uppercase resistor in these two resistors, we're going to call that the load resistor. That's like the washing machine, or that's like the microwave, or that's like the dryer. That's the thing that you want to run. Upstairs here, lowercase r, that's what we call the internal resistance. That's inside the battery. That's a part of a real battery, and that's what's abstracted away in an ideal battery. Ideal battery doesn't have an internal resistance. A real battery does have an internal resistance. So the property of an ideal battery, I've summarized it here. Property of an ideal battery is that no matter what current you draw from the battery, so you might draw 1 milliamp, tiny current. You might draw an amp, that's quite a big current. You might draw 1,000 amps. No matter what current you draw from the battery, it always supplies the same terminal voltage. Even if you, with an ideal battery, you draw at 1 million amps or 1 billion amps from the battery, that would be ridiculous. But the ideal battery would supply the same terminal voltage. Now, real batteries aren't ideal batteries. So real batteries, the more current you draw from the battery, so suppose you draw 1 milliamp, then 1 amp, then 100 amps, then 1 million amps. The more current you draw, the less terminal voltage you get. And the less terminal voltage you get because some of the EMF supplied by the battery is being used up inside the battery by the internal resistance. And so that's what you're seeing in the comparison of these two diagrams. The EMF supplies is the voltage supplied by the battery. It's the electromotive force supplied by the battery. And if you look here in this circuit, no matter what resistance we put down here, and no matter what corresponding current we draw, this resistor always sees the full voltage, the full EMF of the battery. But in this circuit on the right, again, downstairs here, this is the washing machine or the dryer. No matter what resistance we put here, no matter what current we try and draw here, in this case, the more the current we draw, the less the battery voltage we see, because some of it is used up on the internal resistor. There's some voltage drop across the internal resistor. And so that's the introduction to the concept of an ideal battery that always supplies the same current, no matter the current you draw. And a real battery, realistic battery, that draws less, has provides less voltage the more current that you draw from it. So I just want to talk about the real battery circuit a little bit. So here's that same circuit. I've redrawn it here. What are the keys to understanding this circuit, to being able to do calculations with this circuit? There's two real keys to understanding this circuit and calculating with this circuit. I've written them down here. So the first key is that there's a current flowing around that circuit. That current flows, that charge flows through the battery, through its internal resistance, and through the load resistance. So it flows across in the circuit diagram, that element we called the EMF, epsilon. It flows through the internal resistance that we called the little r, and it flows through the load resistance that we called uppercase R. All of those components, the EMF, epsilon, the internal resistance, little r, the load resistance, big R, will see the same current. So they all have the same current flowing through them. You can't lose any current or gain any current as you walk around the circuit in this simple circuit. And so that's an important point about understanding this circuit, that all the components see the same current. However, the other important thing about this circuit is that voltage that the EMF supplies, so suppose it supplies 1.5 volts, that voltage is shared in some way between the load resistance, the washing machine, and the internal resistance of the battery. So they share that EMF. They share that 1.5 volts. So maybe, if you were drawing a lot of current from the battery, maybe the load resistance would get 1 volt and the internal resistance 0.5 volt. Maybe if you were just drawing a little current from the battery, maybe the load resistor would get 1.49 volts, and the internal resistance would have 0.01 volts. So they share that EMF that's supplied, that 1.5 volts. And they share it in a way that's determined by the electrical current that's flowing in the circuit. So these are 3 equations, I've listed them here, that describe this circuit in which a real battery is powering a load resistor like a washing machine or like your dryer. So let's just walk through these equations. These equations are basic equations that relate to those key ideas of the sharing of the voltages and the common current through the components. So upstairs here, the terminal voltage on our battery, so that's the voltage across this entire box here that incorporates the load resistance. That's the EMF of the battery, less the voltage that was dropped, we would say, dropped across the internal resistance. So this is a little bit of Ohm's law. The current through this resistor times the resistance of the internal resistor is some voltage. That's the voltage drop across the internal resistance. And we subtract that from the EMF that the battery supplies to get the terminal voltage of the battery. So you can see here exactly, if you increase the current, you get a lesser terminal voltage. If you decrease the current, you get a greater terminal voltage. Here is the expression for the current in the circuit. So this is the expression for the current that flows in the circuit. And if you look at this expression for the current in the circuit, again, this is based on Ohm's law, it says that the current is the EMF that's supplied by the battery divided by the resistances in the circuit. And for this real battery, there's 2. There's the load resistance, the washing machine or the dryer that we know about, and then there's the internal resistance here. And so both of those add together to create the total resistance of the circuit and determine the current that's flowing in the circuit. And then finally, here's an equation describing the supply and dissipation of power in the circuit. On the left-hand side is this power supplied to the circuit. On the right-hand side is the power dissipated in the circuit. And again, you see here, this power supplied by the battery's EMF, so, which is just the product of its EMF and the current. That power is dissipated in a combination between the internal resistance and the external resistance, between the load resistance and the internal resistance. So this is the power in the internal resistor, this is the power in the load resistor. If you look at each of these three equations and think, what would be the situation if we had an ideal battery? If we had an ideal battery, this piece would go away for the terminal voltage. You'd always see the full EMF. If we had an ideal battery, this internal resistance would be 0. And we'd always get this same, and we'd always just see a current that's determined simply by the load resistance of the washing machine or the dryer. And then if we had an ideal battery and we had no internal resistance, then this piece would vanish downstairs here. And we'd just have all the power supplied by the battery being dissipated in the load resistor, in the washing machine or the dryer. Anyway, those are the three equations that sort of accompany the key ideas from the last slide. If you're working through problems with real batteries, you'll be working with these equations that are based on the concepts in the last slide. Let's look at an example of that. So in this particular problem, we've got a real battery. So it's got both a source of EMF and an internal resistance. The real battery itself is in this dashed box here. And we're told that its EMF is 15 volts, but its terminal voltage is only 11.6 volts when we're delivering 20 watts of power to this load resistor, say this washing machine or dryer or microwave. So we're given a bunch of information about this circuit. We're given the EMF of the battery, so that's 15 volts. We're given the terminal voltage of the battery. That's the voltage that gets applied to the load resistor. So the load resistor is seeing 11.6 volts. And then the difference of those two, so 15 minus 11.6, 3.4 volts. 3.4 volts must be the voltage across the internal resistance. So the 15 volts from the EMF is going to get shared. We're told it's being shared. 11.6 volts to the load resistor, and the remainder, I calculated it, 3.4 volts to the internal resistor. So based on that information, we're going to solve for the internal resistance little r and the load resistance uppercase R. Let me do this on the whatever this is called. I've forgotten what its name is now. It's an old timers moment. Forgotten how to switch it on as well. Okay, here we are. I redrew the circuit, and my circuit diagram, you see, has in it the EMF, the internal resistance, little r, the load resistance, uppercase R, and I've added to the circuit diagram. I know the voltage across the load resistor. We were told it directly in the problem, 11.6 volts. We know the voltage across the internal resistance because we were told the EMF. So it's 3.4 volts, because 3.4 volts plus 11.6 volts add to the 15 volts of EMF. And then finally, there was one other little piece of information. We were told that our microwave or our hairdryer or whatever it is consuming 20 watts. So I want to find, the question is, what is the load resistance and what is the internal resistance? When I think about calculating low resistance, internal resistance, I think about Ohm's law. I want to use Ohm's law to calculate the little r and the big R. But if I'm going to use Ohm's law to calculate the big R and the little r, I'm going to need the voltages across the two resistors, the currents through the two resistors. I know the voltages across the two resistors. we're, we're told that in the problem. So I know I call them V subscript uppercase R for the voltage across the load resistor, V subscript lowercase r for the voltage across the internal resistance. I know those, but I don't know the current. And so I said to myself, the first thing I'm going to do is actually figure the current. Then I can apply Ohm's law to the two resistors. So I want to figure the current, and I'm going to figure the current based on the additional thing that was given, the power dissipated by the hairdryer. Okay, so I'm going to figure current because I know then I can solve for the resistances. And the equation that I'm going to use, we met it in last class. The equation for the power dissipated in this case the load resistor is it's not that equation at all, sorry. I heard this quote once. The brain is a fantastic thing. The brain is a fantastic thing. It starts working the moment you're born and only stops working when you stand up here in front of people and start speaking. That's the only time it's not working. Anyway, that was completely irrelevant. But the power dissipated in the load resistor is the current in the load resistor times the voltage across the load resistor. Immediately we see, right, I can solve for the current by rearranging this equation as power in the load resistor divided by the voltage across the load resistor. I know those two numbers, right? The power is 20 watts. The voltage is 11.6 volts, and so if I divide one by the other, I got 1.72 amps. And so that's the current. And so now I'm essentially home and dry, or whatever the expression is. I can solve the internal resistance because I know the current through it and its voltage. I can solve the load resistance because I know the current through the load resistance and the internal voltage. So let me solve for the load resistance. Ohm's law says that the voltage across the load resistance is the current through the load resistance times the resistance of the load resistance. I can turn that around and I can just solve for the resistance of the load resistor by taking the voltage across it and dividing by the current through it. So that is 11.6 volts divided by 1.7 amps. I already figured it out, of course. 6.7 ohms, 6.74 ohms I got. And you can do the same thing for the internal resistance. So the voltage across it, again by Ohm's law, is the product of its current, which is the same, times its resistance, which will be generally different. We can rearrange that and just figure the load resistance by dividing the voltage across the load resistance, which is 3.4 volts, by the current, which is the same 1.7 amps. And when I did that, I got 1.98 ohms. And so that's how we analyze the circuit of a real battery. And that's a very useful thing to do. When you wire up a household circuit, your washing machine can't draw any amount of power. Your microwave can't draw any amount of power. You have to worry about internal resistances as well as load resistances that you apply in real circuits. Okay, I want to move on to circuits with series resistors and circuits with parallel resistors. We'll start with series resistors. And so this is the circuit that I'm thinking about. I'm thinking about where did I put the pen, light pen. Over here, this is a type of series resistor circuit we're going to be focusing on. And just look at it. And think back to the series capacitor circuit that we previously looked at. Here in the circuit is a battery. We're going to think of this as the ideal battery now. And here in the circuit are two resistors, and they're in series with one another. Meaning, again, if you were an electron, imagine that. If you were an electron walking around this circuit from one terminal to the other terminal of the battery, this is a series circuit of two resistors. You're going to walk through both resistors. You have to walk through both resistors. The current has to go through both resistors. That's what we mean by a series resistor circuit. In a series resistor circuit, the equivalent resistor, and by equivalent resistor, and we're going to figure out the equation for this equivalent resistor, the meaning of the equivalent resistor is that if you apply the same voltage to that equivalent resistor, it draws the same current as the pair of series resistors. That's what we mean by the equivalent resistor. If you apply the same voltage to the equivalent resistor, it also dissipates the same power of the circuit involving the two individual resistors. So that's what we mean by the equivalent resistors. It's a useful concept, and we're going to see how to calculate that equivalent resistance and work with that equivalent resistance. Okay, so the key ideas for series circuits involving resistors I've listed down here. My slide's now moved off to the left again. Gosh. So here's the two key points, the two key ideas about this series circuit. Firstly, resistor R1 and resistor R2 have the same current flowing through them, and that's the same current that's flowing through the battery. So the currents through all the circuit components here, the battery, R1, R2, are all the same. So that's a really key idea, important idea in understanding what's going on. The second point is that the resistors R1 and R2 in a series circuit, they share the voltage that's supplied by the battery. So resistor R1 will get some fraction of it, and resistor R2 will get the remaining fraction. Okay, it's like sharing out M&Ms or something. The battery has given them 100 M&Ms, and they're going to share it out in some way. The battery has given them a certain voltage, they're going to share it out between them. So those are two key ideas. Based on those key ideas, the equivalent resistance, this guy here, that draws the same current, dissipates the same power for the same voltage as the two series resistors, is equal to the sum of the resistances of these two guys. And in general, if you had 3 resistors or 4 resistors or 5 resistors in series, then the equivalent resistor is the sum of all the resistors. So this is the general statement. The equivalent resistance with a number of series resistors is the sum of all of them. Now, there's an important point there that when you put resistors in series, you're making a greater resistance. When you put resistors in series, you're increasing the resistance. If you think about resistance as that sort of impedance to the flow of the current, like pebbles with the impedance of flow of water. If you put 2 resistors in a chain, if you put 2 resistors in series, now the current's got to go through the first one. Well, there's going to be some impedance there. Then it's got to go through the second one. There's some more impedance there. So it sounds like the resistance is going to be bigger, and the resistance is bigger. The resistance is the sum of the 2 resistances. So it's as simple as that. Let's look at an example problem with series resistors to get used to working with equivalent resistors for series resistors and Ohm's law in this sort of circuit. So in this particular problem, I have a series arrangement of two resistors. So if we look at the circuit diagram, I've got this 6-volt ideal battery downstairs here. And it's connected to resistor R1, is 2 ohms. Resistor R2, it was 4 ohms. And then a final wire back to the other terminal of the battery. So we've built a circuit that has two resistors in parallel. The battery is providing 6 volts. And the resistors on the left, R1 is 2 ohms, resistor on the right is 4 ohms. So look, these resistors are going to each see the same current passing through them as the battery is supplying to the circuit. These two resistors are going to share the voltage. And they're also going to share the power that's dissipated. And this question asks us to calculate, this is like a laundry list, calculate the currents through the two resistors, calculate the potentials across the two resistors, calculate the powers that are dissipated by the two resistors. We're going to calculate all those things. So we're going to go ahead and do that. Okay. Here we are. Here's the problem, and I started working it out, and I started by drawing the circuit, so the battery downstairs and the two resistors upstairs, and I've denoted the battery EMF as 6 volts, the resistor R1 2 ohms, resistor R2 4 ohms, and there's a current, I called it I, that is flowing through all of these components in this series circuit. A helpful tool in solving circuit problems is equivalent resistances. So I thought I'm just going to solve the equivalent resistance first. Of course, it's simple. It's 2 ohms plus 4 ohms equals 6 ohms is the equivalent resistance of these two resistors in series. So this is 6 ohms. And so that's how I started out the problem. Now we want to find this laundry list of different things. There was the current, there's the voltages, and there's the powers through or across or dissipated by the two resistors. In a series circuit, the current through the resistors is the same. And so it sounds to me like that's a good place to start. In that sense, that's the simplest case. They see the same current. They're not sharing out current. We don't have to figure out the sharing. Let's start with the current because that's the same. So the current through resistor 1 is the same as the current through resistor 2. I1 equals I2. And that's the same as the current through the equivalent resistor, the 6 ohm resistor, if it's connected across the same voltage, the 6 volt voltage. And that current through the equivalent resistor by Ohm's law is simply the voltage across its terminals, which is the 6 volts of the battery, divided by the resistance of the equivalent resistor. And so I can figure the current through the individual resistors by figuring out the current through the equivalent resistance. Because they're all the same, I just got to divide 6 ohms by 6 volts. Oh, that's convenient. 1 amp. So 1 amp is the current through each of the two individual resistors. That was nice and easy. What about the voltages? Now, figuring out the sharing of the voltages between the two resistors actually gets very easy. It's just applying Ohm's law. It gets very easy because now we know for each of the two resistors, we know the resistances of the two resistors, we know the currents through the two resistors. The only thing in Ohm's law we don't know is the voltage across the two resistors. So let's find the voltage across V1 across resistor R1. By Ohm's law, it's just the current through it times its resistance, so I1, R1. We know both these numbers. 1 amp is the current, 2 ohms is the resistance. This is 2 volts. Well, that was easy. We can do the same thing for the second resistor. The voltage across the second resistor, by Ohm's law, is the current through the second resistor. That's I2. The resistance of the second resistor, that's R2. I know both those numbers. It's 1 amp times 4 ohms. That's 4 volts. And so those are the 2 voltages. And you notice there, right? Think about this. The battery supplied 6 volts. We said the resistors would share it in some way, and they are. One of them, the smaller resistance, is getting a smaller fraction of the voltage, and the other one, the larger resistance, get a larger fraction of the voltage. So the 2 ohm resistor gets 2 volts, the 4 ohm resistor gets 4 volts. That's how they've decided to share out the 6 volts that was provided to them by the battery. Now we want the powers through the 2 resistors. That's also easy now. Remember back to the equation for the power being dissipated in a resistor. It's just the product of the voltage across the resistor times the current in the resistor. So for the power dissipated in resistor 1, we just need to multiply voltage and current for resistor 1. We know both these. The voltage is 2 volts. The current is 1 amp. And 2 times 1, I know that. 1 watt. No, I don't know it. 2 watts. So that's the power that's being dissipated in the resistor on the left. And the same thing for the resistor on the right. Power 2 is the product of the voltage across the second resistor, the current through the second resistor. That is, I know this one too, that's 1 amp times 4 volts, so that is 4 watts. So we also see that the 2 resistors are dissipating power, both of them. One is dissipating 2 watts, 2 joules a second. The other one's 4 watts, 4 joules a second. Actually, we could check that if we like. The power supplied by the battery is the product of the terminal voltage of the battery, 6 volts, times the current through the battery, 1 amp. So it's 6 watts. The battery is supplying 6 watts by this same equation, right? Current times voltage. And we see that it's supplying 6 watts into the circuit, and the 2 resistors are consuming that 6 watts. One of them consumes 2 watts, and the other one consumes the remaining 4 watts. So that's good news. We're conserving energy. We didn't destroy any energy. We didn't create any energy. The energy that was supplied by the battery was dissipated into heat, kinetic energy, by the resistors. Okay. I just wanted to show you this water metaphor analogy for electrical current through series resistors. This cost me 1 hour searching on the internet for a picture like this, but I think it's worth it. Maybe not. So this is an analogy to these water flowing over these steps. Is an analogy to current flowing through series resistors. Think of each step as a resistor. So the water flow is the water current is the analogy to the charge flow or the electrical current. The drops with each step is an analogy to that's a change in gravitational potential. A drop in gravitational potential is analogous to the change in electrical potential or drop in electrical potential across resistors. And what you see in this picture for the water current down these steps is that the same current flows through all the steps, right? But the steps share the height drop, the gravitational potential energy drop from the top of the staircase to the bottom of the staircase. That's exactly the same in the electrical circuit, right? The resistors all saw the same electrical current, but they shared the electrical drop rather than gravitational drop from one end of the circuit to the other end of the circuit. And so this does look like, is an analogy or a metaphor for the electrical current in a series circuit. Okay, let's talk about parallel resistors, or resistors in parallel. So here's the circuit that we're going to be interested in on the left-hand side. And here's the equivalent circuit that's going to be a useful tool for us. So on the left-hand side, I've now got two resistors again, R1, R2, but they're now arranged in what we call parallel. And you can remember back to the parallel circuits with the capacitors. So in parallel, it means, again, think about being an electron. And your job is to go around this circuit from one terminal of the battery to the other terminal of the battery. In this circuit, right, you're either going to go through resistor R1 from one terminal to the other terminal of the battery, or you're going to go through resistor R2 as you travel from one terminal to the other terminal. So that's what we mean by a parallel circuit. The concept of an equivalent resistor for this circuit, again, the meaning, the idea of an equivalent resistor is it's the single resistor that you could replace the pair of resistors with. And if you apply the same voltage, you draw the same current. If you apply the same voltage, you dissipate the same power as the two individual resistors. So again, that's in all these, when we use these term equivalent capacitors, equivalent resistors, what we mean is if you replace the parallel or the series circuits with the equivalent capacitors, equivalent resistors, for the same voltage applied, you draw the same current or you store the same charge. For the same voltage applied, you dissipate the same power or you store the same electrical energy. That's what equivalent resistors, capacitors means. Okay, so again, there's two keys to understanding the parallel circuit. Like there was two keys to understanding the series circuit, and here are the two keys. So one of the keys is that whatever voltage you apply to this circuit with two parallel resistors, that voltage is applied to both the resistors. So the battery's voltage here is applied across resistor R1, just connected to the terminals by wire. It's applied to resistor R2 because it's also just connected to the terminals of the battery. So here the two resistors are seeing the same voltage, and it's the battery's voltage. In the last case, the two resistors were seeing the same current, and it was the current through the battery. So that's an important distinction, important difference. The other important distinction, important difference, is that in the previous case of the series resistors, they shared the voltage of the battery. In this case, the parallel case, these two resistors share the current that's coming from the battery. So resistor R1 gets some fraction of the current, and resistor R2 gets the other fraction of the current. So those are the keys to understanding the circuits. And then the other important ingredient in working problems with these circuits is what is that equivalent resistance? Like for the series case, what was the series resistance? And here's the equation for it. The reciprocal of the equivalent resistance for this parallel circuit is simply the sum of the reciprocals of the individual resistors that make up the parallel circuit. Here's the equation if we got two parallel resistors. But in general, right, if you've got 3, 4, 5, or whatever number of parallel resistors, the equivalent resistance, the reciprocal of the equivalent resistance, is equal to the sum of the reciprocals of all the individual resistors that are in parallel with one another. So an important point here, that again is kind of the opposite from the series case. In the series case, you put two resistors in series, you make a bigger resistance. There's more impedance to the current flow. If you put two resistors in parallel, you make a smaller resistance. So this actually makes a smaller resistance. There's less impedance to the current flow. It's like you're giving the electrons, those little electrons that swarm around the circuit. You're giving them two opportunities, two ways you can go. Like giving traffic two ways to go. There's now two streets instead of one street you can drive down. So at commuter time, right, 9 a.m. in the morning, whenever I get up, it's going to be less crowded because there's two roads to go through. And the same here. There's going to be less impedance to the current flow because there's two opportunities, two paths back to the other terminal of the battery. Okay, let's solve a circuit problem with parallel resistors. And all I did was to disconnect the original circuit from the last problem and reconnect it as a parallel circuit. That's what I've done over here. So if you look at this circuit, it's a parallel circuit involving R1 and R2. I've connected them to the terminals of a 6-volt ideal battery. We're not going to worry about internal resistance. And R1, the first resistor is 2 ohms. R2, the second resistor is 4 ohms. And we're going to be asked to figure out the voltages across the resistors, the currents that are drawn by the resistors, and finally the power that's being dissipated by the resistors. Those three things. Same three things. They're not very original, I know. Same three things as the last problem. So let's go ahead and do that. Okay, so here I am. I wrote out the problem, and then I drew the circuit. I want to draw the circuit because that's the picture on which I'm going to frame my understanding of the problem and build up my solution to the problem. The circuit diagram, or diagram is always important. Sound like my own grandfather there. Anyway, stop reminiscing and get on with the problem. So I drew the circuit and I've labeled it with the values of the resistors and the value of the EMF. 6 volts, 2 ohms, 4 ohms. I know, again, that this equivalent resistance is a useful tool in solving circuit problems. So I'm going to calculate the equivalent resistance. The reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistors. So one of them was 2 ohms, so that's a half. One of them is 4 ohms, that's a quarter. A half plus a quarter is 3/4. So this is 3/4 inverse ohms, because these are equivalent inverse resistances. So actually the equivalent resistance itself is 4/3, 1.33 ohms. So that's our equivalent resistance, and we're going to work with that. Now again, where do I start in solving this problem? I'm going to start by actually calculating the voltages across the resistors. Because again, that's the thing in a parallel circuit. They have the same voltages. That's the simplest thing. The currents is a little bit more complicated because they share the currents. So in the series case, we started with the currents because they had the same currents and they share the voltages. In this case, we're doing the reverse. We're going to start with the voltages because they have the same voltages and then work on to the currents, which they share. So the voltages is really easy in this one. The voltage across resistor number 1 is the same as the voltage across resistor number 2. It's simply the voltage that's supplied by the battery, because they're simply just connected to the terminals of the battery by wire. So those two voltages are 6 volts. That's also the voltage, let me just write it down, that's across the equivalent resistor. Okay, Now we want the current. So if I want the current through resistor number 1, I1, I'm going to think about, again, Ohm's law. That's the relationship between the current, the voltage, and the resistance. So the current through I1 is the voltage across I1, that's delta V1, and divided by the resistance, that's R1. And if I plug in the voltage, 6 volts, divided by the resistance, which was 2 ohms, that's 6 over 2, and that's 3 amps. So that's the current through the first resistor. We can do the same thing for the second resistor. Current through it, I2, is the voltage that's across it, delta V2, divided by the resistance of it, that's R2. And that is let's see, what did I say? 6 volts divided by 4 ohms, so 6 over 4, 1.5, 1.5 amps. So those are the two currents. So you see that they are sharing the current. There's actually a total of 4.5 amps passing through the battery, and 3 of those amps goes through the lower resistance resistor because it's easier to pass through it. 1.5 of those amps is going through the higher resistance resistor because it's more costly to pass through that. Let's look at the power dissipated. The power dissipated in resistor number 1 is delta V1 times the current, I1. So voltage times current will give us the power dissipated, the joules per second. I know both of these. It's 6 volts times 3 amps, 18 watts. And for the second resistor, the power, P2 I'll call it, is, again, the voltage drop across that resistor, delta V2 times the current through it. That's 6 volts again, but this time times 1.5 amps. So that's 9 watts. And so they're both dissipating power. And if we were to calculate the power supplied by the battery, which is supplying 4.5 amps, 6 volts, if we've been multiplying those, we would discover it's the sum of these two. It's 27 watts is being supplied by the battery. So the battery is supplying some energy again, and the resistors are dissipating that energy. We're not losing or creating energy. We're not violating any massive laws of physics and discovering new things. We're just transporting the energy around from the chemical energy that was stored in the battery to ultimately thermal energy in the resistors. Let me just compare one point here. Look at this series circuit. We've got 9 watts and 18 watts. Total of 27 watts. Sorry, this is parallel circuit. Look at this parallel circuit, get that right? We're consuming a total of 27 watts between the two resistors. In the series circuit, that was this guy here, we consumed a total of only 6 watts. So the series arrangement consumes less power. The parallel arrangement consumes more power. That's because the series arrangement had a greater equivalent resistance, so it could draw less current. The parallel arrangement had a lower equivalent resistance, so it drew more current. And so there's a big difference in the power dissipated in the series and parallel arrangement because there's a big difference in the equivalent resistances, and the big difference that corresponds to a big difference in the currents that are drawn. I want to just show you a demonstration of these two circuits. Okay, so I've just put 200 volts across this. This is called the lamp tree. It is an extremely dangerous demonstration. Because, as I have found in the past, it is not hard to actually, connect your hands across the terminals. But right now what you're looking at is a series circuit of two resistors. Over here on this side of the lamp tree, this is at, say, 0 volts. Over here on this side is 200 volts. So we've got a potential difference from a giant power supply beneath the bench that is providing 200 volts to the lamp tree. And you're seeing, you're not seeing that there's current flowing through these series resistors. There's the same current flowing through this one on the right as this one on the left. They're sharing the voltage, so that 200 volts is shared 100 here and 100 there. And you're actually seeing the power being dissipated through the brightness of the lamps. So that reflects the power, the brightness of those lamps reflects the power being dissipated in the circuit. So it's kind of try and remember how bright they are. They're sort of, they're kind of, not too bright, I would say. They're kind of relaxingly bright, something like that. Okay, so now this is the bit that, scares me. And this is especially where it scares me, where it doesn't fit and then I have to fiddle around. Come on, get in there. Straight up here. Oh, I finally got it. Okay, so I'm making a mess of it, but I'm also making a parallel circuit. So I put these two in parallel now, but of course there's nothing here, so there is no complete circuit. So I have to put this final piece in. I'll put it down here. It looks like it'll fit. Seeing sparks. So now this is the parallel arrangement. So remember, in the parallel arrangement, this 200 volts that I've dangerously applied to the two ends of this, there's both across the top bulb and across the lower bulb. So they're getting the full voltage. You see how brightly they're glowing compared to the previous case. So this is showing you that when you put the resistors in parallel, you're going to make a smaller resistance. You're going to draw more current. You're going to dissipate more power. When you put the resistors in series, you're going to make a larger resistance, which means you're going to draw less current. You're going to dissipate less power. And so we're seeing that here. In these cases, the two resistors, the two lamps, are the same resistance. So they share equal. They have equal brightness, power dissipation, current draw. Okay. This is the analogy for the parallel, the water analogy. The water, I love my metaphors. The water metaphor for the parallel circuit. So this path of this river here, you can think of as one resistor. This path is a second resistor. So in this analogy of parallel resistors, we want to think about parallel water currents. We want to think about the gravitational potential energy drops from, the upstream to the downstream end of the river. So you see here that the two paths, R1 and R2, they're sharing the water current. Just like in parallel circuit, it shared the electrical current. But the two paths have the same height drop between one end and the other end. They have the same potential energy, gravitational potential energy drop. So the gravitational potential energy drops from here, where we start the two paths, to over here, where we end the two paths. Those are the same for the two paths, but they share the water current flow along the two paths. So it's a complete metaphor analogy for electrical current through parallel resistors. What am I doing? Okay. Here's a quiz question. Here we got a parallel and series circuit, and I'm just asking you to compare the power dissipated in the two circuits. Why am I walking around with that thing? So on the left, we've got a parallel arrangement of two resistors. On the right, we've got a series arrangement of two resistors. The one on the left is circuit A, parallel. The one on the right is circuit B. And the question is simply, which circuit consumes the greater power, or do they consume the same amount of power? I feel like I've just, completely told you the answer to this problem. And so I'm not going to give you any time whatsoever. Well, the computer will give you time. Obviously, after that entire demonstration, the two lamps in parallel here were much brighter. They were consuming much more power. The two lamps in series were much dimmer, and they were consuming much less power. So the parallel circuit's consuming more power, the series circuit's consuming less power, because the parallel circuit has a lower equivalent resistance, and so draws more current. The series circuit, higher equivalent resistance, draws more current. The other reason is I want to get onto this problem. Okay, so real-life circuits don't just have a pair of parallel resistors or a pair of series resistors. Of course, they have all sorts of combinations of parallel and series pieces, parts in the circuit. And so we have to learn how to solve circuit problems where we've got more complicated arrangements of resistors that are both parallel and series. And here's an example of that. So if you look at this circuit here, it's a circuit that contains a battery, so source of energy, source of power, source of EMF, source of current flow. And then it has a bunch of resistors. There's 5 resistors here. And those resistors draw current from the battery, and they share the voltage supplied by the battery in some way that you'd have to calculate by understanding this arrangement of parallel and series resistors. And that's what we're going to do in this last 10 minutes. So the question says, firstly, calculate the equivalent resistance of the entire circuit. That's going to be a very useful thing to do here. Then it says, calculate the current that's supplied by the battery. If we've got the equivalent resistance, that's going to be a pretty easy thing to do. And then it says, calculate the potential difference between points A and B. This is the thing, to me, that looks the scariest. That looks the scariest because, my gosh, you've just picked out 2 random points in a circuit, and you want me to figure out what fraction of that 25 volts is between those 2 places. That looks like a big problem. It's not as big a problem as we might think if we take this path, if we take the right path to solving it, which is finding the equivalent resistance, find the current that's drawn by the circuit as a whole. Then we'll find that finding that potential difference is not so difficult. So let's see how it works. I'm going to stay on the slides for this one because there's no way I could write down all the numbers and get it right. So this is me with my therapist, and I'm discussing all the anxieties that I have and so forth. And that's sort of analogous to this problem in a way, because I think of my therapist as there's this dough ball of threads in my head, and she's kind of winding them up and sorting them out for me. Anyway, that's what we're going to do with this electrical circuit. It looks like a complicated jumble of resistors that's incomprehensible by anybody other than Einstein. It's not. It's not. We can understand it if we break it down into smaller pieces and understand those smaller pieces and then kind of reconstruct them in a way to solve the problems, the questions that were asked. So that's basically the plan. The way it works is, as I say, that circuit is some sort of general arrangement of series and parallel resistors. We're going to break it down into parts where we can see, oh, look, that's just a pair of parallel resistors, or that's just a few series resistors. We can find out the equivalent resistances of those pieces, of those parts, ultimately work our way to one equivalent resistor for the whole circuit. That'd be fantastic. Once you've got the one equivalent resistor for the whole circuit, then it just becomes to solve any other problem about the circuit, about, what's the voltage across this, or what's the current through that. It's just a matter of using Ohm's law. It just becomes like the simple examples of the two parallel or series resistors. Once you've got your equivalent resistance, you can start batting away other problems with Ohm's law. Just using it time and time again to solve whatever you like. So we're going to see how that works. Okay, so here's my calculation of the equivalent resistance. This is why I'm not going to draw it on paper. That would be a complete disaster because I tried it. Anyway, so here's the original circuit. And if you look at the original circuit, it had 5 resistors in it and a battery. And so I've labeled the 5 resistors R1, R2, R3, R4, and R5. And what we want to do is turn upstairs here, which is where we're starting, into downstairs here, a single equivalent resistor. So how are we going to do that? So you start looking at the picture, and you start looking for places where you just see a portion of the circuit diagram that's either simply series or simply parallel resistors. And then you figure the equivalent resistance for that little piece, that little series parallel piece. So in this particular case, the example would be with the original circuit. Look, the 4 ohm and the 5 ohm, they're just in series with one another. If I just think about this portion of the circuit, I've got a R4 and R5, a 5 ohm and a 25 ohm, in series with one another. I can replace those, I'm thinking, with a single equivalent resistor. Because it's R4 and R5, I'm going to call it R45. That is 25 ohms. And so that was my first step there. Just made that little change. Just applying my rules about series resistors. Then I started thinking, well, now I've made that change. These 3 resistors here, R2, R3, R4, 5, they just look like they're all in parallel with one another. I could replace them with a single equivalent resistance that represents the effects of all 3 of them together in parallel and further reduce the circuit. And so at this point, in my second step, you can see it here. I won't go through all the math. The idea is simple. That the single equivalent resistor, equivalent to these 3, is its reciprocal, is the sum of the reciprocals of R2, R3, R4, 5. So that's that equation there. If you plug in all the numbers, right, we know R2 is 10 ohms. We know R3 is 5 ohms. We know R4, 5 is 25 ohms. You get this number here, about 2.9 ohms. You notice this is much smaller than any of the individual resistors, because when you build them together in parallel, you're going to make a smaller resistance. That's in comparison to when we put these together in series, we built a greater resistance. Anyway, now I'm getting more comfortable because I've got this circuit here. This circuit here just contains that original resistor R1, and then this single equivalent resistor, which is the combination of all these. Because it's a combination of R2, R3, R4, 5, I called it R2, 3, 4, 5, and that's 2.9 ohms. And of course, now you see that this is just a series arrangement of 2 resistors. I can replace this with one equivalent resistance, which is just the sum, because they're in series, of the 10 ohm and the 2.9 ohm resistor. I get 12.94 ohms. So that's how you can break down a complicated circuit with a battery and then a bunch of resistors in some weird combination of series and parallel. You can always break it down into a single equivalent resistor, if it's got one battery in the circuit. You can always break it down to a single equivalent resistor by applying your rules about series resistors, parallel resistors, until you've kind of contracted the circuit mesh down into one equivalent resistor. So we now know that whole circuit has a resistance of 12.9 ohms. Then things start to get kind of easy. We can just start using things like Ohm's law. So supposing I want the current around the circuit, well, let's just think of that equivalent resistor, 12.9 ohm resistor. I've just got a 12.9 ohm resistor across the 25 volt battery. I can use Ohm's law to figure out the current that's being delivered by the battery. So Ohm's law will tell me that the current delivered by the battery is equal to the voltage, EMF of the battery, divided by the resistance of the circuit. I've just got to divide the 25 volts voltage that I'm supplying by the 12.9 ohm resistance of the entire circuit. That just gives me a current. It's 1.93 amps. And so that's solved for the second part of this problem, which is what is the current that's flowing through the battery. Flowing through the battery and then heading off into the circuit and flowing around the different portions of the circuit in some way that we don't know all the details of yet. So that was the second question. Then finally, here's the third question. The third question was the impossible one. Right? What's the potential difference? What is the voltage between these 2 points A and B? Well, those 2 points A and B are really just the difference. They're just located between the single resistor R1 and the resistor that was the combination of all the other resistors. So this is a second equivalent circuit. It was on our way to finding the full equivalent circuit. It was the one where we just got down to 2 resistors. So I went back to think about this. And then if you go back to think about this, this becomes an old problem, right? That we've already solved in a previous example of 2 series resistors. This is a voltage supplying current to 2 series resistors. The same current is flowing through each of the resistors, and they're going to share this voltage. When we figured out how they share the voltage, in the previous example we worked out the current that's flowing through the resistors. So there's 1.93 amps flowing through this guy, 1.93 amps flowing through this guy. If I want the voltage between A and B, which is where this resistor is attached to, I can just find the voltage across this resistor here by Ohm's law. The voltage across A and B is the voltage across this resistor, which is the current through it times the resistance of it. We know the current through it is the current from the battery. We know the resistance of it. We previously calculated it's 2.9 ohms. We get 5.67 volts.